I mentioned in the earlier video that work and energy are closely related. So let's just take a little bit of a closer look at work. When we change the energy of something, when we climb a wall at a rock climbing place, we do work on ourselves, or work is done because we've converted some chemical energy in our body into some gravitational potential energy. We've changed energy from one form to another. So when we change the energy of an object in any way, we say it either has work done on it or that it's doing work. So we use this notion of work, which is different to the everyday notion. You know, if I'm going to work and doing something, I can feel like I've done a lot of work, but in fact, if I say push a piano or push a car along the road for 20 meters, I haven't actually done any work because I haven't changed its gravitational potential energy. I've just moved it from one point, which is whatever the radius of the Earth is, so 6,400 odd kilometers from the center of the Earth, to another point that's also 6,400 kilometers from the center of the Earth. I haven't changed its gravitational potential energy at all, so I've done no work on it. Now, in fact, I probably have, because I've overcome some frictional forces and so on to make it move, because otherwise it would be easy, and it's not easy. So I've clearly done something, but I haven't done net work. I haven't changed its energy in some way that is continuous or meaningful for it. In other words, if I'd pushed it up a hill, then I would have done work on it, and it would have the ability to do work by rolling back down the hill and running into something or whatever, or having a dynamo connected to it, right? If I'd pushed it up a hill, I would have done work on it, but if I push it horizontally, I haven't done work because I haven't changed its energy. So when we're just pushing on an object against a force, so in this case, there might be a force of friction, and we'll talk about friction in a later video as well. We are overcoming that, so the work done is the force times the distance. And sorry, I'm getting a bit hesitant because I realize that there's an error in this slide, which is the W equals FD, that's blue in the second bottom line. The F should be a capital F because it's a force. We need to try and be consistent with our units. I suspect that PowerPoint tried to help me out with autocorrect grammar and broke it for me, which it tends to do. So work equals force times distance, and then power is the time rate at which work is done. So we talked about rates several weeks ago when we were talking about velocity, speed, and acceleration. They're rates at which we cover distance or change our velocity. Power is the rate at which we do work, so power equals work over time. I could have actually put little deltas on that and said power equals the change in work over the change in time, or the overall work done. Slightly confusingly, the unit, I should have said that I did say in the earlier video, but the unit for work is the joule, the same as energy, because we're just changing energy. The unit for power is the watt, which is a lowercase watt named after James Watt. Slightly confusingly, it has the symbol capital W, which doesn't mean work, it means watt. So in these kind of problems, be aware yourself of the symbols that you're using, and be aware that this is a common issue that students have. They confuse one capital W with another capital W, quite understandably. So just being aware of that. And a watt is not very much energy. Not very much power. 1 watt is not very much power. So we often talk in thousands of watts, kilowatts. It's a more convenient unit. So for example, household power we measure in kilowatt hours. How many kilowatts of power have I been delivering for how many hours? That's a reasonable sort of unit. So you might remember, I'll get out of the way, this photo of my old motorbike from a few weeks ago. And you remember that I mentioned that it can do 0 to 100 kilometers an hour, or 0 to about 28-ish, I believe I was saying, 27.8 meters per second in 3.5 seconds. So I want to find out how much power my motorbike's really got. Say somebody told me that this has 100 horsepower. I want to find out really whether that's the case. So let's check it out. So the work done, it starts off stationary. So it's kinetic energy, half mv squared is equal to 0 when it starts, because v is 0, v squared is 0, that whole thing goes to 0. So when it's doing 27.8 meters per second, we need to know the mass. So the bike is about 250 kilos. It's a big old clunker. And I'm about 90 kilos. I'm a big old clunker. So about 340 kilos total for the two. And if you calculate that as the blue calculation there, it's about 131,383 joules of work. So we could have used kilojoules as well. We could have said 131.4 kilojoules to make it a bit neater, but let's make it a big unit. So this is the change in energy is from 0 to 131,383. So that's the actual work done. That's the W. And then to calculate the power, we know the time, 3.5 seconds. So power equals work over time, 131,383 divided by 3.5 gives 37.6 kilowatts, or 37,538 watts, and then rounded. Yeah, that should maybe have been rounded to 37.5 because the next digit's a 3. 37.5 or 6 kilowatts. And just for funsies, you can go online. A kilowatt is roughly about 0.75 of a horsepower. You can go online and there are good converters. So I did that and converted it and found that it's just a tad over 50 horsepower. Now hang on, they sold me this bike saying it's 100 horsepower, but it's only 50, even at its best and fastest possible acceleration. Well, if you think about it, what you're actually talking about there is a horsepower curve. So if we have a graph of revs on the bottom and power up the side, the horsepower curve typically for a bike is up and down. So at a particular number of revs, that's its maximum power. That's the 100%. But you're not sitting at that number of revs for all of your acceleration from 0 to 100 kilometers an hour. So in fact, 50 horsepower is probably about right because it's an average, because as your revs change, your power changes. And so over that period, and then as I said in the brackets at the bottom there, you're also in an acceleration run. You can't put all the power to the ground, otherwise you will flip, front wheel will come up and you'll be over on your back, or the back wheel will spin. So you put as much power to the ground as you can, but it's not going to be that peak 100 horsepower, that's 75 kilowatts, because of all of those kind of variables of the actual physical situation. So the ideal versus the real in physics world. We won't talk about electrical power right now because we haven't been talking about Ohm's law and voltage and current and power and so on. So we'll talk about that in weeks 9 and 10 when we are talking about electricity. But electrical power obviously is one of the most important forms that we use in our lives.